Okay, good. Well, glad to be here, remote. I don't see you, but so I've been asked to speak about lessons from two grand challenges. So we discovered D3R at the stage of Grand Challenge 2. And as you can see from my title slides, we are mainly dealing with macromolecule in my lab. So we are mainly dealing with proteins, nucleic acids, and ligands. Small molecule docking is something we have been doing a little bit, but that's not the core business. And for us, participating to D3R was a big learning experience. So I'm going to give you a short introduction of what we are doing actually. And then I'm going to go into the lessons, hard lessons that we learned from Grand Challenge 2, and then how we learned from a mistake for Grand Challenge 3 and got actually quite some nice results there, mainly post-prediction and a little bit about binding affinity. So what we are doing in my lab is we are developing a software called HADOC, which is an integrative modeling platform, which is aimed mainly at, again, macromolecular complexes, protein-protein complexes, nucleic acid, peptide, all of that, but can handle as well small molecule. And what we are mainly using in HADOC is we try to gather as much information as possible to drive the modeling process. So we are not into really ab initio docking game, but we try to make use of information, experimental information, but also bioinformatics, all kind of information to really drive the modeling and limit the search problem in docking space. And we can handle more than 2 molecules at the same time, actually. So that's also a feature of HADOC, and we have ways of imposing symmetries when you go to large system. And in terms of Grand Challenge, we have been participating since 2003 now to the Capri Grand Challenge, which is critical assessment of predicted interaction. So this is mainly protein-protein, protein-peptides, and we have shown good performance consistently over the year with our approach. So what are we doing? The search in HADOC is based on energy minimization molecular dynamics. In the first stage, we treat the molecule as rigid, and the docking is done by energy minimization, driven by the data that we put in, typically. Then we apply some simulated annealing protocol with flexibility at the interface of the complex to optimize the poses, and at the end we solvate the entire system in water and do a very short molecular dynamic simulation, extremely short, which optimizes a bit the energetics but doesn't change much the structure in itself. So this is implemented in some kind of, say, workflow control at the Python level, and we use CNS, which is related to Explore, which is related to Charm for the structure calculation. So we have a large user base. Most of the people are actually using the software with a web server. Sorry, Pat. There is a local version, but the server does actually much more. And I don't know if you see my mouse on the screen. We did a survey, this is 3-4 years ago, and we asked people, what are you doing actually? And we realized that quite a large fraction of people are doing small molecule docking using HADOC. So we build in the ability to deal with small molecule to mainly represent cofactors in proteins, but this also enables automatically the docking of small molecules. So how are we going after small molecule docking? So we need some information to guide the docking because it's a driven search. So what we typically do is to define the binding site in the receptor. And we have a concept of ambiguous distance restraint. So in the first stage, the receptor is basically attracting the ligand in a pocket. And in the second flexible stage, the ligand is kind of free to sample the receptor cavity of the binding pocket. We use OPS parameters on the protein sites, and for the ligand, probably, I don't see your face, it's probably good because a lot of people will critical choice of prodrug as a way of generating topologies and parameters, but it has been doing the job in a rather quite automated manner because it's built beyond the portal. We are actually evaluating now the OPLS parameters as well. It doesn't seem like it's improving things at all. And we have ways of dealing with buried binding sites by reducing interactions, but this is all very technical. So we have been doing some internal testing of, okay, how well can we doing with small molecules, and we took the Aztecs non-native set. So it's not really an unbound receptor, but it's a receptor bound to some other ligands. So it's cross-docking type. And the results were kind of okay, if you look at those numbers. But one thing to mention here is that we had the right conformation of the ligand, and that helps a lot. So then we discovered in 2016 or 15, the first round of Grand Challenge 2. Actually, we discovered it after it was started, so we had not so much time to start playing with that, but we say, okay, let's go for it. We've been doing Capri for a long time. Let's put our software to the test. So the challenges here, and you're all aware of that. So the pocket in this case was quite buried. Our starting point for docking are molecules that are separated in space and randomly rotated. So we'll have to get the ligand inside the pocket in this case, so that has its own challenge. And there's a lot of conformational changes on the receptor as well. Most of the work has been done by Zeynep and Panos has been the key person for Grand Challenge 3. So how are we dealing with the ligands? This is again not our core business. We had to learn how to convert a small string into a 3D model. So we use OpenAI for that, and also to sample conformations. So we generate, typically we sample in the order of 500 different conformations. We do a clustering and we select representative structure from all the clusters. And we give this ensemble of molecule to Haddock. So Haddock can deal with an ensemble of starting configuration. So we are not doing n docking runs from n molecules. We do one docking run for an ensemble of molecules. So this was the way we dealt with the ligand there. For the receptor, we just went into the PDB to look at what else was out there, selected representative proteins after clustering on the pocket, harmonize the receptors if needed, and then define a binding pocket which we need to drive the docking in Haddock as the union of all residues that were within 5 angstrom of the ligands that were present in those receptors. And this was pretty much the receipt that we follow. And when we look at some of the first results, we were very pleased. So these were, what I would say, in our hands, quite successful dockings, or at least reasonable quality. But when came the results of the evaluation, the green bar is where we are standing. So that was not very fantastic. We didn't even look at the poses, so we didn't have time to that. So we just selected what the software was giving. So some of the poses probably were not even in the pocket. So, well, that was a learning experience. But so we at that time we also looked at what was the limiting factors. So in dark green our stage 1 performance, and we evaluated, is it the structure of the ligand which is limiting us in our docking, or is it the structure of the receptor? So if we do simply bond-bond docking following the same protocol, these are these magenta bars, it's kind of okay. Okay, we get around 80% success rate on this data set. And we see, compared to what we did initially, if we use the bond ligand, this is where, or the bond receptor, sorry, the blue bars that you see here, this is where we have the largest win. So we learn here that we have to select much in a better way the receptor that we're using for the docking. And the way we did that is, again, selecting and also talking to people and reading some papers. So we needed to select the receptor that has a ligand which resembles most the targets that we have to dock. And for the ligand, and we use the Tanimoto coefficient to do the selection. For the ligand, we upsample the major cluster if possible, but we didn't do much more at that time. And if you do that, so we are comparing our stage 1 performance, the initial performance, and then what you see in green will be the performance after doing the smart selection of the receptor. And this is, of course, improving. You see that in general, the distributions have lower values, so we are improving the quality of the sampling in this case. We can also look at the scoring and the sampling together. So in this plot, we have the FXR different ligands in the x-axis, and on the y-axis will be the top 100 poses returned by Haddock. So if you see a dark gray or black bar, it means that these are kind of acceptable model, near native. So it was not for static. In some cases, we do sample them, but we don't score them. So one example will be here, this one. So this one we completely lose. If we do a smarter choice of the receptor, this is the picture. So now you see that we have much more black, also lower in the plot, meaning that they are scoring better, but we also increase our sampling. But we still have a scoring problem. We see that in some cases we do get good solutions, but we simply don't select them. So this is where we were standing. So the lessons from the Grand Challenge 2 for us was we need to be smart in selecting the receptor. That's crucial. We need to have a better way of selecting the ligand conformations for the docking, because even if we have a bit of flexibility in our protocol, it's hard to get the right answer. And also, we need to have a better ways of starting the protocols, basically the starting conformation of the molecule with respect to each other, rather than the random separated molecules. So this brings us now to Grand Challenge 3. So did we learn the lessons? So that was I don't need to introduce it, of course. So we look for templates in the PDB with at least one bond ligand. And then we compare the ligands that we had to dock to the template, to the ligand in the templates using the maximum common substructure. And we selected the receptor for docking, which has the most similar ligand. So this was what we learned, or lesson 1 from Grand Challenge 2. And this is the best similarity that we could find for the different targets for catepsin. For the ligands, we did basically the same. So we do generate 3D ligands, and we do sample conformations, but then we try to select conformations that we generated that are the most similar to the most similar ligands that we have from the PDB. So we use shape and color Tanimoto, and we use rocks to do this selection, and you see here 2 examples. And we select systematically the best 10 conformers that have the highest combined score. So this is our ligand selection lesson 2 from Grand Challenge 2. And a starting conformation, so we don't do the randomization of orientations and separate the molecule. No, we want to superimpose the selected conformers onto the crystallographic ligands that are in the templates, and we use shape TK for that. And in our protocol, we don't do a rigid body-body docking anymore. We forget about the simulated annealing protocol. We only perform a gentle refinement in explicit solvent, which is addressing lesson 3. In stage 1B, where we had the bond from the receptor, we also kept water molecule in place and over small molecule, but in terms of performance, it didn't make much difference, if any, in our case. So these are the docking results, and you see now that we have many more points that are low in those graphs. So we have RMSD on the y-axis and the different targets on the x-axis. Just some example. This is a nice one. That one is not the best ranked pose actually, because there is basically 2 clusters of solution. So we do cluster of solution, so there are 2 clusters. Here is another example. This one, the scoring works fine because the best cluster is indeed at the bottom, and we have another solution which is much higher. And here, that's the higher solution, which is a different conformation, obviously. So does the ligand similarity have an impact on the quality of the results? Good thing I didn't put any correlation coefficient after listening to Pat's talk, but there is the uncertainty plot there. Basically, there is a little bit of a correlation, but it's not really significant. So we have cases where the similarity is quite high, but still we don't select or generate the right poses. We have cases where the similarity is quite low, but still we get good results. So that's not very conclusive. So did we learn our lessons? So it seems that we've been doing much better than in Grand Challenge 2. So we have the green bar down there, and there's a number of groups or methods, because there are multiple submissions per group, I understood. So this was much better. So we were very pleased when we saw those results. So we have improved, we have learned a lot, and we have improved our way of modeling those complexes. Now a few words about binding affinity and ranking. So we didn't change anything from Grand Challenge 2 to Grand Challenge 3 in what we have been doing. So the structure-based prediction in Grand Challenge 2 was done using an atomic contact model. So we have developed in the past such a model, which was residue contact model for binding affinity of protein-protein complexes. So we train a model based on small ligand data at an atomic level, and this is where it was placing us in Grand Challenge 2. And at the time, we also developed a ligand-based only method, which was using, I'm going to come back to that, and it was not fantastic, but it was in the middle of the distribution. Now in Grand Challenge 3, if we look at our structure-based model, which is contact-based, it's not doing very well, it's down there. So there's another green point that you might see here, up here, at second position, that's the ligand-based model. So ligand binding affinity ranking. So we basically train a single value regression model using target-specific ligand similarity, and we train the model on ligands that belongs to the target. So the model is not general, but it's target specific. So this is where this puts us for the CATS challenge. So it's doing reasonably well, although it's 0.35, so we can discuss if it's good or not. For the kinases, there is many more data that you can use to train the model, so the performance is even better there. And you see that, so these are very simple and fast model. Most of the time here is just spending collecting the data for the training, and then the prediction is extremely fast. So in conclusion, for us, D3R was really a catalyzer to learn from failures, because we didn't do so well in the first round. And the success factors for round 2, or actually Grand Challenge 3 in this case, was really to do our selections of both ligands and receptor in a much smarter way. And this we also realized by talking to people who are in a small business, small molecule docking business. And smart positioning of the ligand in the binding pocket also made a big difference. So we should probably now go back to the targets of Grand Challenge 2 and see if this would have made a huge difference, and vice versa as well. Maybe test our Grand Challenge 2 protocol on the target of Grand Challenge 3 and see how we can further improve things. So this is the team in Utrecht. Well, it's already a one-year-old photo. I mentioned Zeynep, who is here on the right side of the photo, and Panos, who is the one on the top. That's me, because you cannot see me. I hope you see my pointer. And our work is supported by different European and national projects. And of course, I want to thank the D3R team for running the show. Thank you very much.
Okay, I have time for one question. Okay, can you come up here and speak?
So Alex, a very good talk. I have one question. Would the availability of the crystal structure help your binding affinity prediction or not? Maybe I missed that part.
So in Grand Challenge 2,
yes,
it did help. Actually, the prediction that we submitted for the structure-based prediction in Grand Challenge 2, we did, by mistake, we used the unbound structure model. So we would have improved our performance in Grand Challenge 2 if we had used the bond form. In Grand Challenge 3, we only did the ligand-based for all the kinases. And for the first stage, I don't think we tried predicting. I don't think that it would have made much difference in this case. Again, the structure based for the cadepsin size was really crap. So it was really bad. So the ligand one was the best one.
Thank you.
Okay, thank you again, Alexander.
Okay.